There you go. All right, so if you're having to watch this video from home today, we're going to look at finishing problems up related to V is equal to I times R, and we're going to look at high voltage lines. There's going to be a video or two that I show on the screen. Doesn't work the best when I'm video recording of a video, but that's okay. Do your best with that. We're going to look at two types of currents, and then we have some reading questions to be able to look at. Yesterday, we were going through, and if memory serves, we solved two of these problems. Is that correct? Yeah. All right, so I showed you the little triangle thing that some students like to use. If you were gone yesterday, the relationship between V, I, and R can be summarized with this little triangle. Obviously, we did more yesterday than just this, but if I have voltage is what drives current, current is a flow of charges, and resistance is something that restricts the flow. The relationship is that V is equal to I times R. I would be V over R, and R would be V over I. So your goal here is just to make sure that you identify what the correct value is in that equation and then determine the other thing. We did this one yesterday. Today we're going to do 4 and 5. Current in a microwave, 6 1/4 amperes. Resistance of the oven circuitry, 17.6 ohms. What's the potential difference across that? So if I do nothing other than just make a little list, you might find that this is enough to be able to help you identify what to do with that equation. So I is the symbol that we use for electrical current, 6 1/4 amperes. Another way of saying that is that that's 6 1/4 times 6.25 times 10 to the 18th electrons every second. So again, ampere is a coulomb per second. The resistance, I think yesterday we measured the resistance of that little graphite, pencil to be about 7 ohms, and we measured Jack's resistance to be in the neighborhood of 30 or 40 mega ohms. So the resistance here is 17.6 ohms. If I want to calculate then the potential difference, I would use V is just equal to a product of I times R. I multiply those two numbers together, 6 1/4 amps multiplied by 17.6 ohms, and that gives me a voltage of, since it's plugged into household voltage, it should be close to about 110, 120, so 6.25 multiplied by 17.6. Sure enough, I get 110 volts. On the quiz, Friday, I would expect that you know the unit for each kind of quantity. So electrical current measured in amperes, resistance measured in ohms, and voltage measured in volts. Number 5, color television draws 2 1/4 amps or 2.5 amps. When connected to 115 volts, what's the effective resistance? Again, you might just make a little list. I is equal to 2.5. V, potential difference, is 115 volts. And I'm looking for resistance, so R then would be equal to V divided by I. Again, I would expect that you can use that equation. V is equal to I times R to be able to solve for the thing you're looking for. R would be a ratio of V to I, so 115 divided by 2.5 amperes. And that gives me 115 divided by 2.5, 46. You have to write it about 3 times to get it to show up on that board, but that's okay, about 46 ohms, okay? Again, folks, I would not expect that you're going to have too much trouble with that equation. You just have to, it's 3 variables. You're given 2, you have to determine the third. All right, other things we need to look at. Raise your hand, you've ever wondered why birds can stand on high voltage power lines and not get electrocuted? You always wondered that? That would be let the record show no one raised their hand. I've looked at that, I'm like, wait a second. How does that happen? So I'm going to show you that today. Power lines are typically at 100,000 volts or more. So how can a bird stand on a wire and not get electrocuted? There's 2 things. First one, really simple. Current is going to take the path of least resistance. That's a thing of nature, right? things are always going to take the path of least resistance. Well, the resistance of the bird is much greater than the resistance of the wire. So the wire itself is a very good conductor, the bird not so much. And so the current is much more likely to just flow through the wire than through the bird. The other thing, see if I can get back to this. The other thing is that voltage isn't what drives current. What drives current is a difference in voltage. Both feet, or both talons, if you will, of the bird are at the same potential, roughly. Which means, since each is at 100,000 volts, there's no driving force. There's nothing trying to push charges through that bird's feet, simply because they're both at the same voltage. Now, I want to show you a quick little demonstration of this. It doesn't work the best for video recording, but I'm going to try it. And I'm going to ask you guys to come up here really quick, and I'm going to try not to, since I'm going to do this on a video recording that I might place on YouTube, I'm going to try not to have anyone's face in this. So if you are at this front table, I'm going to ask you to get out of the way a little bit. And then as I do this recording, I'm going to do it right up here on this table. Come on up for a few minutes so you can see us a little bit closer. And then hopefully this will work. And again, if you're having to watch this from home, not the best way to learn things remotely using videos. But all right, so here we go. We're not looking. I don't want anyone's face in this. So, okay, back up a little bit. Back up a little bit. I don't want it. Oh, Biswas, you look like you're close. Get out of there. Get out of there. All right. Now, this little demonstration. I'm going to try to, I need 4 books from over on that table. 4 books over on that table. Bring those over. Scrap that. I'm just going to leave these 2. I'm just going to do it. Don't worry about it. Yeah, that's good. All right. Now, I like to think of voltage as height. And you might remember from yesterday, that, where's my little bucket? My bucket around there? Just throw it to me. You literally threw it there. All right. So voltage is like the height of the hill. And so what I did here is I have 2 books there. Each book I'm going to say is at 50,000 volts of potential. So that means if I have 2 of those books, that side would be at 100,000 volts. This side would be at 100,000 volts. These are the 2 legs of the bird. You notice that each leg is at 100,000 volts. What that means is that there's no difference in potential to drive charges. So, since each one is at 100,000 volts, nothing moves through that. Now, how could I get those balls to actually roll down? What would I have to do? Say one more time. Okay, so I'm going to tip the board. I'm going to put one side down at 0 volts of potential. And when I put one side down at 0 volts of potential and the other side is at 100,000 volts of potential, zoom back in there, give me a zoom that doesn't remove that focus. You guys notice that then there is a difference in potential, and that difference in potential causes those things to sort of flow downhill. So in order for me to have current flow, I have to have a difference in potential. And so that difference in potential is what drives current. Since each foot is at 100,000 volts, there's no driving potential. Now, we're going to talk about different types of current today. This right here is called direct current. Direct current flows one direction. It's like a river flowing downhill. Those little balls that are moving represent electrons. The screws that are screwed into that board would represent like maybe atomic nuclei. Maybe this is a copper conductor. It could be an aluminum conductor. The aluminum nuclei stay stationary. And as the electrons move through there, they collide with those nuclei. All those little collisions gives off heat. Did we fry a pickle yesterday? That heat was generated from electrons colliding with stationary pickle nuclei. Now, there's no such thing as an actual pickle nuclei, but those nuclei are not moving, the electrons are. Now, this kind of current is what we call direct current. Would you guys agree that if I increase the voltage, that would increase the rate of current flow? Would you guys agree with that? If V is equal to I times R, I is V over R. So if I increase the voltage, that makes those things move more rapidly through there. Again, another analogy for that. This kind of current is called direct current. This is an alternating current example. Alternating current, what I'm doing is I'm taking the voltage and constantly alternating it back and forth. And as I do that, all I'm doing is I'm causing those electrons to vibrate. that vibrating set of electrons are able to transmit energy through those collisions, but nothing really goes anywhere. They just sort of oscillate back and forth. When I hooked that pickle up yesterday to 120 volts, all I was doing was I was taking the electrons that were part of that pickle and causing them to oscillate. I wasn't moving them anywhere, they just moved back and forth. Okay? That's the idea behind electrical current and why that bird is relatively safe. Head on back to your seats if you would, please, folks. Great. No faces were put on that video. So that means I can place it. No one did any photobomb, did you? Where you like jumped in there quick? You didn't do that, did you? Good. So I want to be able to put that on YouTube. All right. If you're near a down power line, you should either hop or you should shuffle your feet away. And the reason for that is something called a step potential. Now, you guys did the electric field interactive, right? And when you guys placed electric charges on a map, you saw the electric field sort of diminished with distance. You guys recall seeing that? Same idea happens here when I have a downed power line. So I'm going to show you a video. A video of a video doesn't work the best. But the idea here is that maybe that power line comes down and hits right here. Well, you're going to see a radiating field that drops from maybe 100,000 volts down to 0 over a distance. You want to be careful there because if you start to walk away, you don't want your feet to be walking across a really high, if you want to think of it like this, a really high hill. If I have 100,000 volts being spread out over 8 meters, you're going to see that there's a big difference in voltage from one step to the next. You have to be careful on how you walk away from that. I'm going to show you a little video to help you sort of understand that. So again, hopefully this will work for us. Just a quick little cautionary thing. This video is made in Australia, and they're going to give you some numbers to call. Don't call these numbers here in the US. They won't work. Go ahead and grab the links. Okay. Okay, I don't want to play that game. Skip. Okay, good. So frustrated. Give me a second. How do I get this thing full screen? I can't scroll. Oh, there it is. Okay. Oh! I'm no longer frustrated. Now, how do I play it? Spacebar? You're awesome. Thank you. That's not the number for us. Okay. Again, video made in